Okay, I guess we can get started now. Welcome everyone to this session of PNS SSD course here at ETH. And please, if you have questions, you can both put it in Zoom chats for the ones who've joined in Zoom and also YouTube chat. I will try to also check that part. And please, if there's any problem with audio or video, please let me know, but so far things seem to be working. So I am Nika Mansouri-Ghiassi. I'm a third-year PhD student here at Sapphire Research Group. Oh, I am seeing that I need to admit student. Okay. I'd like to see if I can do that automatically so we don't interrupt the lecture. So please give me a moment. Okay. Okay, I guess we can then get started. So today I'm going to talk about GenStore, a high-performance in-storage processing system for genome sequence analysis. This is a work that me and my collaborators here and across different institutions have published at ASPLOS 2022. We'll go through it in more detail today. Okay, so genome sequence analysis is critical for many applications, such as personalized medicine, outbreak tracing, as we've seen over the past years, and evolutionary studies. Genome sequencing machines extract smaller fragments of the original DNA sequence known as reads. Basically, when you have a DNA sequence as your input, these genome sequencing machines read them in like small parts because they cannot read them as a whole. So these smaller fragments that get extracted in terms of like DNA alphabet, so we call these things reads. So in order to have any analysis of the data that we have obtained, we need to perform an operation called read mapping, which is the first step in genome sequence analysis and aligns reads to potential matching locations within the reference genome. So if we have a patient or some other, let's say for other organisms, the data collected, and we want to gain some biological information out of it, we align these reads to basically to a reference genome, which we know already. For example, this is a human reference genome on average, represents a person without, let's say, specific biological issues. And then like you would align these reads to these reference genome. And then for each location that these reads match to, we perform an alignment step to find the degree of similarity or alignment score between the reads and the reference genome at those locations. So calculating alignment score, basically finding differences between the read and the reference exactly. So that requires a computationally expensive step called approximate string matching, or ASM, to account for differences between the reads and the reference genome. So these differences then can represent sequencing errors or genetic variations. And then based on that, biologists or healthcare providers or other scientists can draw conclusions or, like, let's say, provide personalized medicine or perform outbreak tracing, as we discussed in the previous slide. So however, as we discussed, this operation requires computationally expensive approximate string matching. And then the read mapping operation performs this alignment on large genomic data sets, for example, containing millions of reads. Therefore, read mapping is both computationally expensive and also incurs high data movement overhead. So there has been significant effort, specifically over the past couple of years, into improving read mapping performance due to its importance in the applications we discussed and beyond. So prior works have tried to improve it through efficient heuristics, hardware accelerators, and various filters that prune reads that do not require this expensive computation. At different parts of the stack, let's say in compute-centric or cache-centric, or like through solutions near main memory. While these approaches address the computation overhead in read mapping and data movement in these sections, none of them alleviate data movement overhead from storage, whose impact becomes even larger when the other overheads and computation overhead gets alleviated. So our key idea here in this work is to filter reads that do not require the expensive alignment computation in the storage system to fundamentally reduce data movement overhead of read mapping. Examples of reads that do not require that costly alignment step would be exactly matching reads to the reference genome that do not need approximate string matching performed during alignment, and non-matching reads that have no potential matching locations in the reference genome, and therefore they can skip the alignment step. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and limited hardware resources in the SSD. So by addressing these challenges, we propose GenStore, the first in-storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. And GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So that was a summary of what we're going to be seeing in this talk. Let's start with the background on read mapping so we can dive into the talk and the design of GenStore in more detail. So mapping reads to the reference genomes can be expensive due to the expensive computation on large data sets. And the search space in the reference genome can be very large. For example, the human reference genome contains more than 3 billion characters. Therefore, read mappers typically use an index of this reference genome to reduce the search space. This index contains unique K-length subsequences of the, which we call them K-mers, that are extracted from the reference genome. And also this index has the locations of these K-mers in the reference genome. So how do we look up this index? So read mapping is a three-step process usually, and the state-of-the-art mappers involve several heuristics to reduce the cost of expensive alignment computation. So let's see what these steps are. In the first step, which is called seeding, we want to determine some potential locations in the reference genome, or called seeds, that we can that the reads might potentially align to. So instead of going through those 3 billion locations and check one by one, we want to already find some candidates. So how do we do that? We extract some K-mers, these K-length subsequences that we talked about. So they extract these K-mers, so it can be like, I don't know, let's say 15 mers or like 19 mers. So K can be different numbers. Here, for example, for sake of this example, I'm showing 3 mers. So we extract these K-mers out of the reference genome, and we look up each of them inside the index. And for the K-mers that have that hit in the index, we mark their locations in the reference genome as potential matching locations or seeds. Then for the next step, we want to see if we can basically prune some of these seeds. So the next step is called seeding, or seed filtering or chaining, that prunes the seeds in the reference to which the read would not align, using a simple approximation of this alignment score. So we perform like a more high-level operations that are more computationally, let's say, cheaper, and then we would then go prune some of them. And at the end of this step, the reads that have all their locations filtered, then they already can skip the third stage, and the other ones go to this third stage for the remaining reads, which is the costly alignment step, and that one determines the exact differences between the read and the reference genome via that expensive approximate string matching that we talked about. So that was the high level, let's say, typical steps that conventional read mappers would use. Okay, so we perform experimental studies in our work to understand the potential of efficient in-storage filters for improving read mapping performance. We perform a case study on real-world genomic read datasets on various read mapping systems and state-of-the-art SSD configurations. And we make several observations. First, the ideal in-storage filter significantly improves performance by reducing data movement overhead and also reducing computation overhead. So it reduces both of these things. And also filtering outside SSD relatively provides lower performance benefit because it does not, first of all, reduce data movement overhead from storage. And secondly, it must compete with read mapping, main read mapping operations from filtered read for other system resources because it's performed outside the storage. So it can compete from storage, external bandwidth, main memory bandwidth, and compute resources. So also we observed that a hardware accelerator based on state-of-the-art hardware read mapping accelerator is proposed in the literature. So we observed that this reduces the computation bottleneck, which further makes I/O even a larger bottleneck in the system. So basically what that means is that in-storage parsing can provide a lot of benefits for read mapping, and that benefit would increase because a lot of works have previously focused on various overheads and other parts of the system, so relatively now the impact of I/O is increasing. So motivated by these observations, our goal is to design an in-storage filter for genome sequence analysis in a cost-effective manner. And we have three key objectives in designing our new system. First, the system should provide high in-storage filtering performance to overlap the filtering with the read mapping of unfiltered data. And second, the design should support reads with different properties and different degrees of genetic variation. And third, it should not require significant additional hardware overhead. And to this end, we propose GenStore, which is the first in-storage processing system designed for genome sequence analysis. And our idea here is to filter reads that do not require alignment inside the storage system and send the unfiltered data to the host system for further processing. However, as we discussed, so filtering reads in modern SSD can be challenging. So that is actually due to different workload behavior across read mapping workloads and the limited hardware resources in the SSD. We will dive into them in more detail in the next slides. So now let's take a look at filtering opportunities based on the input reads. So sequencing machines that we talked about at the very first slide, so those, based on their technology, produce one of two kinds of reads. Either they are highly accurate, but shorter, and then either they're less accurate and longer. So reads, based on these, we leverage two filtering opportunities. First, we can matching reads, which are reads that match exactly to one or more matching basically subsequences of the reference genome and do not require approximate string matching during alignment. So these things can frequently happen in short reads that have low sequencing errors and also low genetic variation. For example, humans, reads from humans can, let's say 80% of them on average match to human reference genome because in general, we have low genetic variation, let's say compared to viral samples or like bacterial samples. So then we have these non-matching reads. So we can, such reads do not have, let's say, any potential matching location in the reference genome. Let's say after stage 2 in read mapping, all the potential matching locations received will be filtered. So then we can skip the expensive alignment step that happens in the third step. So examples of such reads that of non-matching reads can frequently occur in long read sets with high sequencing error rates or with high degree of genetic variation. For example, with virus samples, as I mentioned earlier. So by thorough analysis of this read mapping process for reads with different properties and different degrees of genetic variation, we designed two low-cost and storage filters. One is GenStore-EM for filtering exactly matching reads, and GenStore-NM by that filters non-matching reads. So let's take a closer look at this GenStore-EM. GenStore-EM accelerates read mapping by using an efficient in-storage filter to filter reads that have at least one exactly matching location in the reference genome via simple operations without requiring alignment. The key challenge in GenStore-EM is the large number of random accesses to large data structures inside the SSD. So why would this be challenging? So large data structure, let's say you want to access the index, and this index can be large, and it is very expensive to do that inside the SSD. So why is it the case? So first, NAND flash memory exhibits poor performance for random access reads, and there is limited DRAM capacity available in SSD, which is relatively small compared to the size of the data structures that need to be accessed. So to reduce the number of accesses per each read, we introduced read-sized k-mers. Therefore, instead of having, basically, as this is like we see, instead of extracting several k-mers per each read and performing index lookup for each of them, we can use the whole read as one k-mer and have only one index lookup per read. So the number already decreases. And to avoid, let's say, random accesses to this index, we introduce the sorted index of these read size k-mers. So when you sort the index, then we can sequentially scan this read set to find the exact matches. So we can basically perform that via sequential scanning of the read set and the index together, so avoid fully random accesses. So let me show you a key idea of GenStore-EM with a simplified example in which each short read consists of 10 characters. So usually this can be around a few hundred characters, let's say 150. But now, for the sake of simplicity of this example, I want to show a read that has 10 characters. Suppose that we have two data structures. So a sorted read table, each entry of which stores a read and its unique ID, and a k-mer index, which contains all unique read-sized k-mers of the reference genome. So if you remember, initially when I was giving a background, I talked about the k-mers that we extract from the reference genome. Here, again, we do the same, but here k-mer is bigger. So where was I? Okay. So that has this like a sorted k-mer index, which contains all unique read-sized k-mers of the reference genome, along with each k-mer's corresponding location in the reference. So that is, again, similar to the past. The difference only being the k-mer size, and also each data structure is sorted by read and k-mer in alphabetical order. So why couldn't we sort the index before? Because for each read, we would extract several k-mers. We needed to go to different parts of the index all the time. So we couldn't sort, depended on the k-mers that were existing in the read. But here we only have one k-mer, so we have only one access anyways. So we can already sort these k-mers in advance, since we have one access per read. Yeah. So let's go through how we find actually a match in this. Exactly, we want to find an exactly matching read. So we sequentially scan through these data structures in 3 different ways based on the comparison result of the current read and k-mer. First, when the current read and k-mer are identical, we record the read as an exactly matching read that can be filtered from further read mapping process. So then we move to the next element in both of the arrays. Okay, so if the read is alphabetically larger than the k-mer, we conclude that the k-mer does not match any read because we have been sequentially scanning, right? So if we already had a k-mer matching to the read, we would have found it. So if the k-mer is smaller than the read, it means that the k-mer would not match any read. So we just can move to the next element. Okay, so then now the k-mer is larger than the read. So again, we conclude that the read this time does not match any k-mer in the index. So when it doesn't match, we know that, okay, we need to send it to the read mapper. So this read mapper can happen anywhere, right? It can be a hardware accelerator outside SSD, or like processing in memory accelerator, processing cache accelerator, anywhere, or like even a software read mapper happening in, let's say, executed on the host CPUs. This can just go to the read mappers outside. So then we can go to the next read and examine the next read. So using this simple sequential accesses and this technique, GenStore-EM avoids random accesses and performs filtering using only simple low-cost logic, which was for comparison. So despite the key benefits that I talked about till now, that is sorted read size k-mer index will provide. This index actually takes up a larger space. So 126 gigabytes, 126 gigabytes for human index as an example. So this is because of the large number of unique read size k-mers. So imagine we have here 150 mers, whereas in baseline we would have 15 mers or like 19 mers. As you can imagine, the number of unique elements is very large, and also each element on its own is very large. So to further reduce the overhead of GenStore-EM, we replace the read size k-mers with a strong cache of each read that can act as sorting criterion and fingerprint of each entry. So these hash values would take a smaller space. And then again, we can use this to sort the reads, right? Because now we don't have to sort the k-mers, because we don't sort the k-mers on their own now. And we also do that for the reads too. So we basically, instead of having these strings as sorting criterion, now we have these hash values. And that can also act as their fingerprint. So using strong hash values instead of the read size k-mers reduces the size of the index by 3.9 times. So this is still larger than the baseline k-mer index used in conventional read mappers, but our proposal is feasible for in-storage processing due to the large capacity and high internal bandwidth of modern NAND flash-based SSDs, because you can distribute this data nicely and across different channels access them. So that shows actually example of this hardware software co-design performed in this work, because what happens basically is that we analyze this application deeply, And based on the underlying hardware that we want to architect it for, we also come up with these, let's say, algorithmic optimizations. So in a sense, this hardware-software co-design enables us to achieve basically the benefits that GenStore provides by considering these factors. Basically, the opportunities and limitations of the hardware we're architecting for. So now I show the overall operation flow of GenStore-EM with a sorted read table and sorted K-mer index in the NAND flash memory, distributed across all channels and dies. So when the data is evenly distributed across all these channels, dies, and planes, we can leverage this full internal bandwidth of the SSD. And here we have a comparator logic on the SSD controller, small added logic. So GenStore-EM consists of two steps. Step one reads the two data structures from NAND flash chips to the SSD's internal DRAM in a batched manner. So instead of bringing the whole data structure, since we're sequentially reading through it, we can bring small batches like a few hundreds of megabytes each time in the DRAM, and then the capacity would be fine then. Then step two performs exact match filtering within each read batch using simple comparator logic. Basically, we bring these batches, then we compare reads and K-mers sequentially, as I showed you in previous slides. Okay. Step 1 and 2 are performed in a pipelined manner. And since they work in different batches, when you finish with the batch, you can already send it to the host system for performing the read mapping. So therefore, during filtering, GenStore-EM can send the unfiltered reads to the host system for full read mapping operation. And meanwhile, concurrently, it can work on the next batches without basically using I/O bandwidth or any data movement overhead happening outside when filtering. So now let's take a closer look at GenStore-NM for non-matching reads. Actually, before I go on, is there any question either in Zoom or on YouTube? I pause for a few seconds if you want to ask something. Okay, let's go on then with GenStore-NM. I hope you remember the 3 steps we discussed: the seeding, seed filtering and chaining, and alignment. So using chaining, that second step, GenStore-NM filters most of the non-matching reads, which are reads that would not align to any subsequences in the reference genome. Recall that chaining filter calculates a similarity score for each read called chaining score and filters reads with no high scoring potential matching location. Basically, if a read already has all its potential matching locations filtered, then there's no need to go to the alignment because there's no location to align to. So, but calculating a chaining score in SSD can be challenging, because finding the best chaining score requires performing many iterations of a dynamic programming algorithm for all seeds within a read. And this can be particularly challenging for long reads, since they have a large number of K-mers per read. So they can be like around, I don't know, 1 million characters. So then we need to perform this dynamic programming operations inside the SSD, and to perform it in a performant way, we would need a lot of buffer space and a lot of parallelism inside the SSD so that we can filter these at high throughput, which would incur high cost. So what can we do to reduce the cost of chaining? GenStore-NM uses a lightweight chaining filter that selectively performs chaining only on reads with a small number of seeds. and directly sends the reads that would require more complex chaining to the host system. So why would this be beneficial, or why would we want to do that? So this idea is based on our observation from analyzing a wide range of real-world genomic read data sets. So let me show you an example here. This figure shows alignment probability of a read and a long read data set to subsequences in a reference genome. So that is the vertical axis shows the alignment probability. And this is as a function of number of seeds per read. So we want to see, for example, if a read has here 64 seeds, would it align? What will be the alignment probability? So we analyze this for different genomic data sets from different species, humans, I don't know, bacteria, mice, I mean, like many different species. You can look up in our paper if you're interested. And we observed that reads with a sufficiently large number of seeds are very likely to align to subsequences in the reference genome. And so that is intuitive, right? Because if you have many seeds, basically many chimeras of a read matching into the to the reference genome, then it's high likelihood, okay, that's very similar, so that would likely align. So that is intuitive. And then we show that, okay, after this threshold, it's very likely. Of course, the design can also be set for different thresholds, depending on the organism or how much data you want to filter on inside the SSD. Given this, reads that already have a lot of matching locations and a lot of seeds can directly be sent to the host system for full read mapping and bypass the in-storage filter, because these reads wouldn't filter anyways. So we don't need to invest on performing that operation to see whether they would filter or not. And as you see, this is a minor detail, but anyways, here, based on read mapping heuristics, they also automatically neglect reads that have less than specific number of seeds. For example, here we had 2 or 3 seeds. If the read has less than that, we would filter. So here we have between this lower bound, let's say 2, and this upper bound here, 64. We want to perform in-storage filtering for these things, because then you don't know exactly what's going to happen. And actually, a lot of the reads in various use cases we show fit in this case too. So that can filter a large number of reads between these thresholds. So we conclude that the selective, lightweight chaining approach can filter many non-aligning reads without costly hardware resources inside the SSD. Yeah, okay, here. So I do not dive into the details of it, details of the design, how we exactly perform this chaining hardware efficiently inside the storage system. But if you're interested, please take a look at our paper. We in detail explain how GenStore-NM works. So now let's go through our results. I will pause again a few seconds. If you have any questions about GenStore-NM, EM, genomics, anything, let me know. Otherwise, I'll go to the results. Okay, cool, let's go. We evaluate the following systems. So BASE, which is the state-of-the-art software or hardware read mappers for both short and long reads, which actually shows that, okay, if you have software read mapper or hardware read mapper, we can integrate GenStore with it. So that's why we choose our baseline from various state-of-the-art mappers in software and hardware and for short or long reads. And GS here in the plots I will show you shows a base integrated with GenStore inside SSD. So basically, we want to see how much GenStore, how GenStore augments these accelerators, how much it can improve their performance by integrating with them concurrently, filtering rates inside the SSD. Okay. And we also evaluate these mappers and systems with various SSD configurations. So a low-end SSD, a medium-end SSD, and a high-end SSD. So you might ask, why do we just not only consider high-end SSDs? Why do we consider low-end SATA SSD while we can have, I don't know, PCIe Gen, I don't know, X different generations of PCIe SSDs? So the answer is that in a lot of large scale systems that want to have large scale storage systems, currently they use these lower end SSDs because they are more scalable. So they would take, let's say, the ports, a larger number of them would exist. So therefore you can attach more of them to the system, and also they're more cost efficient. So currently in a lot of these extremely large scale storage systems that which you would use for genomic data sets, they use these low-end SSDs. However, we also include evaluations and results, as we will see, for these high-end SSDs for systems that would use them in, let's say, smaller scale, or for the future, which this will be used in more places. Okay. So we analyzed the benefits of GenStore-EM for a 22 gigabyte short read set with 80% of reads exactly matching to some subsequences in the reference genome, and then can be filtered. So we show the benefits of GenStore on software and hardware read mappers. So GenStore provides 2.1 to 2.5 times speed up compared to the software baseline, and 1.5 times to 3.3 times speed up compared to the hardware baseline. And it also provides an average 3.92 times energy reduction. So now let's analyze the benefits of GenStore-NM for a 12 gigabyte long read set with very high degree of genetic variation compared to the reference genome, where 99.7% of the reads do not match to any subsequences in a reference genome. So now we show the benefits of GenStore on software and hardware read mappers. And we show up to 27.9 times the speed up compared to the software baseline, and 19.2 times the speed up compared to the hardware baseline, and an average 27.2 times energy reduction. We find area and power values of GenStore by synthesizing GenStore-EM and NM using 65 nanometer technology node, and find that for an 8-channel SSD, the area of GenStore is 0.2 millimeters square, and the power is 26.6 watts. And by scaling the area to lower technology nodes, we observed that the area overhead of GenStore is 0.006% of an Intel processor, and less than 9.5% of the 3 ARM processors in a SATA SSD controller. Again, I'm giving this smaller scale example because on a more advanced controller, we would have even more hardware resources. So relatively, this area consumption of GenStore would be even less. So there are other results in the paper. Let me briefly talk about them. You can again check the paper if you're interested for more details. So these results include the following: effective read set features on performance. For example, for data set sizes, we scale them up to 440 gigabytes. And filter ratio, basically, depending on the species, use case, read mapping use case, we show how many percent of a read basically would filter, and then according to that, how much GenStore provides benefits. Let me give you some examples. We consider some COVID-19 data sets to show this like highly evolving, like really quickly evolving species, because since they evolve very fast and the differences between them and the different genomes is actually really large. So the filter, so some data gets filtered again using GenStore-NM. Or when you are in a lab and a human is performing experiments on some sample data set, let's say some data set collected from the Zürich lake, and we want to do experiments on it. So since humans do this data collection, usually you would align whatever data you have, map it to human reference genome to remove contamination. So hopefully only a small amount of data would align, and a large amount of data would be discarded, not aligned to the human reference, because human here is contamination in a sense. So that would be another example we talk about, that a lot of the reads wouldn't align. Also for human data set, I already talked to you and showed the results of it, that since humans are very similar in their genetic information, let's say, so on average, like 80% of the reads would match to the human reference genome. So, and then various other examples. So if you're interested, please check. Then we have performance benefits of an implementation of GenStore outside the SSD. Because we have different optimizations, right? We wanted to see how would those perform if you have them outside the SSD. In some cases, it provides performance benefits due to more efficient streaming accesses as opposed to random accesses to the index. But it provides a significantly lower benefit compared to GenStore, because in the end, the index is like it's large and needs to be streamed outside the SSD. So it we show significantly larger performance benefit for GenStore inside the SSD. We also perform more detailed characterization of non-matching reads across different read mapping use cases and species. I already talked to you about it, some examples of it. So now let me conclude this talk by giving the summary. So as we discussed, there has been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters that prune reads that do not require expensive computation. While these approaches address the computation overhead in read mapping, none of them alleviate data movement overhead from storage, because impact becomes even larger when the computation overhead gets alleviated. Our goal is to improve performance of genome sequence analysis by efficiently and effectively reducing unnecessary data movement from storage systems. And the key idea is to filter reads that do not require the expensive ASM or approximate stream matching computation in the storage system to fundamentally reduce data movement overhead. However, filtering reads inside SSD is challenging because read mapping workloads can exhibit different behavior based on the genomic data that we're analyzing, and there are limited available hardware resources in the storage system. And to this end, we propose GenStore, the first storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. And we show that GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So thank you very much for listening to this talk.